All right, well, welcome everyone. My name is Remy and I'm from Logix Academy, and happy to have you all join with us on our virtual training series and continue to learn at home with our wonderful partners and a variety of topics. Today's session is in partnership with Let's Talk Science, and I'm pleased to introduce to you our speakers, Lynn and Cheryl, in a few moments as we get started with today. Just a little bit of background. Logix is an education company based out of Markham, Ontario, and has 3 divisions. Been working in the education space for almost 10 years now, focused on K-12 STEM, robotics, and coding education. With our first division in education, looking at solutions, software, hardware, curriculum, and professional development for teachers. Our academy is our in and out of school programs for students, and it's all gone virtual now. And then, of course, our consumer product division, focusing on the solutions with our retail partners like Best Buy, Amazon, Toys R Us, and Indigo, and more. You may have been familiar with some of our products spanning from kindergarten all the way to 12, as well as Makerspace. And the nice thing today is that some of these solutions are all for free, virtually using robotic simulators to support at-home learning. So if you have any more questions around that, feel free to connect with us at education@logixacademy.com. Curriculum is core to what we do at Logix. Both our Learn to Code and Code to Learn curriculum, supporting educators in fundamentals in computer science from kindergarten to 12 through a scope and sequence, as well as integration of the curriculum in provincial aligned subjects, math, science and tech, English language arts, social studies, and others. And that's really critical to use these as learning tools and resources in the classroom. Professional development is something is really core to what we do as an organization, whether that's in person, when that was something we did, and hopefully returning soon across the country, and of course online and virtual, and being able to connect and interact with school districts, teachers, students across the country, and even through district and board implementations, and even a provincial implementation in Atlantic Canada. Our community unites all of the educators to collaborate, connect, share their learning and what they're doing. It's a free community for anyone to join, so feel free, if you're interested to learn more and connect and have questions after today, to join our community. And lastly, this training series is something that we started at the tail end of March to really provide an opportunity for teachers to learn in a variety of topics, from remote learning solutions to data science, to robotics and coding, to tools like Microsoft Teams, solutions like Minecraft in the classroom, using Flipgrid, and a variety of other topics. We have about 40 different sessions happening every week, with thousands of teachers participating in our online training. So really excited and appreciate the support of our partners who've been able to provide this all for free for any teacher in Canada, with our partnership through Microsoft, Intel, and folks like Let's Talk Science, who I'm happy to introduce today. So without any further ado, I'm excited to introduce to you Lynn Fitzpatrick and Cheryl, Donovan White, who will be able to share with us the resources and talking about data and data analytics in the classroom. So I'll turn over the screen to Cheryl and Lynn, and I'm excited to learn alongside all of you today.
Thanks, Remy. Can you see my screen there now, okay?
We can indeed, yes.
Okay, great. So welcome, everyone. And that was very impressive, Remy, in terms of what you offer as an organization. And many thanks to you and Logix Academy for inviting Let's Talk Science to be part of this virtual learning and training series. And of course, special thanks to Michelle, Keith, and you for supporting us. So today's session from Let's Talk Science is called Creative Collaborators, Solving Problems Using Data. And we'll do our facilitator introductions in a few moments so you can actually see us. So we really like to thank you for taking the time to learn with us today. And I always say we learn best from our colleagues. So if you have any ideas or want to share any or elaborate on a certain thing that we're doing, please feel free to use the chat feature to do that. We hope you leave today with some good ideas to bring back to your classroom. We're going to, first of all, give you a little overview of Let's Talk Science, just a short one, and then we'll talk about some unplugged coding activities as well as some plugged ones. So hopefully you'll get lots of ideas to bring back. And I always say to my educators when I present face-to-face is, today we're all learners. And as I introduce each activity, think about how it can be scaffolded scaffold up or down for your particular age range of children that's in your classrooms or that will be in your classrooms. So without further ado, we'll get started. Let's Talk Science, as a national charitable organization, is committed to working toward meaningful reconciliation. We believe that acknowledging the traditional territory on where we work and where we live is a small but a very important step in that process. It reminds us to learn more about our Indigenous people in all regions throughout Canada. In that spirit, I would like to acknowledge the land on which I'm situated today, and also my colleague and co-facilitator Cheryl is in Newfoundland and Labrador and is the traditional land of the Mi'kmaq and Beothuk. And we encourage each of you to reflect on where you live and where you work and how you can contribute to reconciliation in your own way. So I'm just going to turn on my video just for a moment as I introduce myself. My name, as I said, is Lynn Fitzpatrick. I'm located in Marystown, which is on the Burin Peninsula of Newfoundland and Labrador. And I'm an educational specialist with Let's Talk Science for about 6 years now. And I really enjoy professional learning and sharing ideas. So I'm going to pass it over to my colleague, Cheryl, to introduce herself.
Hi, everyone. I'm Cheryl Donovan-White, and like Lynn, I'm an education specialist for professional learning with Let's Talk Science, and I work from a home office in Conception Bay South, which is just outside of St. John's. So I guess we'll get on with the webinar. And the very first thing that we want to let you know is that if at any point during the webinar you have any questions, you can post those in the chat feature, and we'll do our best to answer those before the end of the webinar. And I'm going to turn my camera off. So who is Let's Talk Science? Well, we're an award-winning national charitable organization, and we've been providing engaging evidence-based STEM programs for more than 25 years at no cost to Canadian youth and educators. Our national office is located in London. We also have an office in Calgary and one here in St. John's, Newfoundland and Labrador. We also have partnerships with 50 post-secondary institutions, and we have over 3,900 volunteers who work with us to provide programming. So why do we do what we do? Well, I think we all know that science and technology are changing the world in which we live and we work and we play. And some of these students who are in your classrooms or sitting across the screen from you now, I guess, will be working in jobs that don't even exist yet. So how can we prepare them to work in those jobs and to become good global citizens when we don't even know what those jobs are? Well, by enhancing scientific literacy, by focusing on skills and competencies and supporting their learning through STEM, we can help prepare them for those jobs by providing them with those skills and competencies, and also help them to become globally engaged citizens. So at Let's Talk Science, we have a number of programs, and they're here from outreach, projects and events, professional learning, which you're engaging in today. We have online resources available as well as research and advocacy. I'm not going to go into each one of these in detail, but there is information on each of these on the Let's Talk Science website, letstalkscience.ca.
Thanks, Cheryl. We start every one of our workshops or webinars with a bunch of statements, I guess, in terms of what we believe, and hopefully you believe the same thing. We believe that students are competent and capable of complex thinking, and therefore, as educators, our role has to change to be a co-learner or co-constructor of knowledge with children. As Cheryl said, the world is changing, and when I went to school, we sat in classrooms and we took notes down and we learned the notes and we regurgitated them back on tests. And 5 minutes later, it was all forgotten in terms of what we actually put down on the paper. So we want children engaged and doing science, doing STEM. And therefore, if we believe that the students are competent and capable of complex thinking, students are actually doing the work in terms of talking about what they're working on, manipulating things, doing things, and representing what they know. And then our role as educators is not to impart knowledge, but to support them in discovering their own knowledge. So we respond to them, challenge them, extend their thinking. And what I always say to everyone that goes to a workshop with us is that the best gift that you can give your students when they ask you a question is to say you don't know the answer to something. So then you can become that co-learner. So when they ask a question, you say, I don't know. Let's find out together. And therefore, that opens up a whole new dynamic in your classroom of being that co-learner and co-constructor. So I encourage you to do that with your students. Our learning intentions for today are as follows. We're going to, first of all, give you just a brief overview of computational thinking and the skills and competencies related to it. We're going to look at a microbit as a sensor and really generally sensors in an overview of sensors. We're going to introduce you to a design and build with an actual problem that we're going to suggest, and then how you would work through that in supporting those computational thinking skills and competencies. And really, what we're doing through these webinars and connections with Logic Academy is to connect and engage in meaningful discussions about digital literacy. So feel free to use the chat, as Cheryl said. So what is computational thinking, and what comes to mind when you think of it? If you did a research or did some research on the internet about what does that mean, you'd come up with a whole group of definitions about what it is. We often think about what it means in terms of what students are doing when they're actually engaged in computational thinking. And what you'll see on the left side there are all the skills, or some of the skills related to computational thinking, that we're going to actually explore a little today. Things like logic, predicting things, analyzing things, looking for patterns or similarities in things. And I'm sure, like Rose is on the call today and she's in a grade 1 classroom, she is constantly, I guess, doing pattern, repeating patterns and things with children, which is an example of computational thinking. The whole idea of decomposition, it's a big word, just meaning breaking things down into smaller parts. So looking at a problem and breaking it down into subparts. Abstraction, removing unnecessary detail. In other words, focusing on what's most important. An algorithm, making steps or rules to follow to actually do something. And just think of a recipe where you're actually making cookies, for instance. You have steps involved and things you have to do to actually produce the cookie. So that's an example of an algorithm. And then, of course, having students evaluate what they do, making judgments on it. And we really explore those skills and enhance those skills through different approaches. And we're going to share some things with you today in terms of some approaches that we found very successful, creating or designing and making something. And we're actually going to design and build a seed saver today, virtually. The whole idea of debugging, looking for errors in a program or what you're doing and fixing it. Collaborating, of course, is a skill that we want children to have, and being able to work together. Persevering, and this is like, I have 3 grandchildren, and what I often find is that they don't stay on trying to figure out something when a problem is presented to them. They kind of give up easier. And I think from talking to other educators they find the same thing. So that whole idea of perseverance, keeping going, and being like an engineer in that you might produce something or design something and make something, but it might not be your best product. So you want to go back and persevere and redesign it, keeping going. And the whole idea of changing things to see what will happen, tinkering with things. And of course, I'm sure all the educators on the call really, when they see global competencies, it's an integral part of each provincial framework documents now. And really, when you look at the 6 C's here, and a lot of times, I think a couple of years ago, they were called the 4 C's, and then they expanded it. But they are the I guess, overarching attitude, skills, and knowledge that we want children to have graduating from school or going from grade to grade. I want my grandchildren to be good critical thinkers, to be creative and innovative, to really self-learn, learning to do or learn on their own, and, start a question and try to find the answer to it. And of course, with today's pandemic and people doing schooling from home, that is so, so important right now. The whole idea of being able to collaborate with others and communicate well with others and where they are in the world in terms of their citizenship. So we're going to start just a brief overview of some unplugged activities that we're going to share with you now. And I'm going to pass it over to Cheryl. And unplugged, of course, you can do anytime, anywhere without a computer device. So I'm going to pass it over to Cheryl to talk about the cup stacking challenge.
Okay, with the cup stacking challenge, you'll see the photo that's there, the picture. You'll need your students to work in groups of 3, and one of the people will be the robot, one will be the programmer, and one will be the recorder, and they're going to be stacking these cups. Now, there are pictures and cards that they'll have, and we'll provide you with a link to a digital handout at the end where you can access all of these resources and print them for yourself. So what would happen is the robot would wear a blindfold, and I know that can be tricky in some cases, so that's optional. If they just want to close their eyes, that's fine. The programmer is the one that chooses the stacking card, and they give the robot instructions on how to stack the cups to form the structure that's on the card that they've chosen. And your programmer can only use certain commands, and here are the commands: to pick the cup up or put it down, to move the cup forward or backwards, to turn it clockwise 90 degrees or counterclockwise 90 degrees. And your recorder is the one who's going to write down the program as the programmer is going, giving it to the robot so that they can construct the structure. So I'm going to hand it back to Lynn so she can talk about another unplugged activity.
Another excellent one that I guess really focuses on the skills of patterns and using directional language and sequencing and that algorithm, that skill, is actually graph paper programming. So what would you need for graph paper programming? First of all, students work in pairs, and all they really need is a grid, graph paper grid. It can be any size, and they need some kind of an image on it. And what they're going to do is give instructions to program their partner, and they work in groups of 2, to actually construct that same grid. So working in pairs, students will program each other to draw pictures by coloring in squares on graph paper. One person draws and programs their partner, and the programmer must use the following program commands. And what I often say is that I would, if I was working with a group of students in class, I would ask them to come up with their actual programming key. Because some might want to say, for instance, instead of saying color in square, to actually say, pen down, change color. So get them to actually work with you to come up with the symbols they're going to use, as well as the language that's associated with it. And also what's really nice, and you can do this as well as Cheryl mentioned with the cup stacking, is actually doing it on this programming sheet where the students actually put in the arrows for the directions that they're transmitting to the person who's drawing. And they can also get the whole idea of loops there too, because what they'll realize is that there's sequence, or there's a pattern that they can recognize in different graphic images. And they might want to say, like, go forward 3 steps or 3 blocks and color each block. So explore that in terms of using the programming sheet with students. In your handout or digital handout, you will get some samples, and this is just one of them, of different grid patterns that you can use with your students. So really, why graph paper program equals coding? First of all, they're creating an algorithm in that they're describing how to draw a picture, and they're actually converting the language into symbols. So they're actually doing a program. And there's example as a question mark there. By actually transforming those actions, move 1 square right, for instance, into symbolic language for a right arrow, students are actually coding. So there's lots of extensions to this for scaffolding up and scaffolding down, and you'll see the image there has varied colors in it. So you can use large grids for small children. You can even tape a grid on plastic, for instance, and put it on the floor and get them to actually do the activity. You can use more complex images. You can get students to trade their program, not the actual sketch or the graph paper, but the actual program, to see if somebody can read the program and actually debug it if there's any issues with it, to recreate what they actually started with. As I said, add loops in terms of functions to make the program simpler, adding like a go forward three times or go forward 5 times, whatever. And of course, throw in different colors and add a command to switch color to the programming sheet that they're doing. I'm going to pass it back to Cheryl to talk about directional language activity.
Okay, another directional language activity you could do, it's very similar to in some ways, to the cup stacking that you have 3 people in a group, and again, you have your robot programmer and recorder. And this time you place an object somewhere in the room, and the programmer has to get the robot to that position to retrieve that object. So again, as Lynn said, it's always a good idea to have the students come up with the instructions that they want to be able to use, and to get that so that they're all using the same one. So the recorder jots down the instructions. And another really good thing that you could do with this would be that the groups exchange their programs and see if they can retrieve the object using the program that the other group has laid out. Another thing to be cognizant of here, I guess, too, is the robot should only do exactly what the programmer tells them to do. And I say that because sometimes the robot may anticipate what the instructions are going to be, or anticipate cues that are there, and will move accordingly before they get the instructions. So that's one thing that the robot has to do. And this is an example of another directional language. And Emerald Code is actually a series of STEM-related videos that I guess is targeted at grades 4 to 6 students, and maybe grade 7. And in this case, they're rubber ducking, which is going through that code step by step, and you're explaining it as if you're explaining it to something that doesn't have the ability to think. And instead of providing verbal cues here, what they use are noises. So you can see the beep means to go left, the bell right, a honk forward, and a moo means for them to stand up. And this is just one, and they're very short. This one's only about a minute long. So for all of those directional language activities, one of the things that's very important to, I guess, consolidate learning is to do a debrief. So one of the things that we want to do is ask the students what skills and competencies they were using when they were engaging in these activities. So for example, were they breaking the problem that they had into smaller steps? Well, if they were engaging in decomposition. Were they creating a list of logical steps, ordered logical steps? If they were, it was algorithmic thinking. Did they look for patterns? As Lynn said, you can see the graphic on the screen. There are patterns there, so they're looking at pattern recognition. And did they have to find and correct bugs in their program? And this would be really evident if the groups switched their programs and the other group wasn't able to retrieve the object, for example, or replicate the design and the graph paper. So they're engaging in debugging. And also the competencies of critical thinking, collaboration, and communication that the students were engaging in as they were completing these activities. So let's we want our students not just to be able to talk about these computational thinking skills, but we want them to be able to apply those computational thinking skills to solve problems. So we're going to talk now a little bit about how we obtain data. So there are many ways of obtaining data. One of them is people can manually record things. They'll either do it with, pen and paper or pencil and paper, or they might use a digital device to be able to record their data. Or they can use something called a sensor to be able to gather and record data. So what are sensors? So a sensor is, as the definition says on the screen, a device that detects a type of input from its physical environment. And there are many kinds of sensors, and some of the ones that these are just a few examples. For example, green energy. We walk into buildings now. When we walk in, the lights go on. When we leave, the lights go off. When we put our hands under a tap, the water flows. When we move our hands away, it stops. So those are examples of sensors. Traffic control is another one where large cities will use these sensors to gather data about traffic flow, and then they might do things like change the sequence of lights in that area at certain times of the day, or they might change bus routes at certain times of the day. So some examples of sensors are things that are photoelectric devices that detect level of light, touch. I think of one of those taps you have in your or faucet that you have in your kitchen that you can touch and the water comes on. Pressure, that could be the sensor in the seat of your car that detects that somebody's sitting there and therefore turns on the airbag or doesn't turn on the airbag. Moisture for farming, color, and of course the camera, which detects motion or movement, which we've already talked about. So I'm going to hand it back to Lynn, and she'll talk a bit more about sensors.
Okay, thank you, Cheryl. So I'm going to turn on my video. Hopefully you can see it okay, and you let me know if you can actually see what I'm holding up. Can you see it okay, Cheryl?
I can see it, yes.
Okay, so one of the sensors, or one of the, I guess, piece of equipment that we found very helpful in doing projects with children and with sensors is the microbit. And these are roughly between $20 and $25. And I know a lot of my colleagues here in Newfoundland and Labrador have purchased these, some just for a center, like one microbit for a center in their classroom. Sometimes they can afford to buy a whole class set. But what's really nice about the microbit is that it's very tiny, fits in the palm of your hand, and has built-in sensors that you can build projects with. And we're going to show you an example of a design and build project where we're actually going to use the microbit in a few moments. So what's neat about this is that, first of all, it has, and you can see on your screen there on the left, it has an A button and B button that are programmable. So you can press A and something will happen, press B and something will happen. It also has an ability to connect to the computer through a USB connector. And what's really nice about it is that it can be attached to a battery pack so that this can become mobile. So that if you're using, for instance, and I'll talk about the accelerometer on it in a few minutes, but if you're using an accelerometer and you want to measure the speed of something, say going down a ramp, then you can do it with the microbit and the battery pack. So that's a real cool feature of it. It doesn't have to be connected to the computer all the time. So where are the sensors on the microbit? So we have 4 sensors. The light sensor, what you'll see on the, hopefully you can see the microbit okay here, and you can see it on the screen there as well. There's a 5x5 array of light emitting diodes right in the center there. So there are 25 of them that are individually programmable. So they can detect or display text, they can display numbers and images. And we're going to give you a couple of examples in the next section of actually using those LEDs. So one really nice feature is that it not just can display light, but it also can detect it. So it can emit and detect the light. The temperature sensor is actually on the CPU itself in terms of the covering. So if you lay it in the palm of your hand, that will affect the temperature reading. So we're going to give you a little program in a few minutes about temperature, but it's very important that your hands don't touch the surface because that would affect the sensor that you're, or the temperature that you're trying to determine. It also has an accelerometer over here. So as I said, it can detect speed, and also has a compass that can determine direction, northwest, east, and south. So really neat, nice feature for the microbit. So what do you use the microbit with? There's a free program called MakeCode, and you'll see it there on the screen now, makecode.microbit.org, that works in parallel with the microbit to actually program it to do certain things. And when you go to, as I said, it's free. When you go to makecode.microbit.org, you'll land on this page that you see there now, and you can start a new project. But what I was new to all this just a few months ago. So I just started experimenting a little bit by trying some of the tutorials down at the bottom, and there's a whole bunch. I'm just showing you a couple there. So you can try like a flashing heart, or making a name tag, or rolling a dice. And this will be able to be programmed to do that, and then actually see it working. So I encourage you that if you're feeling a little bit anxious about doing some coding with your students, some of you might be far along in the process, I don't know. But if it's just an introduction or anything, let them take it and do it. And I tried this with my grandson, who is only 6. And I just showed him a couple of the tutorials. I didn't go through them. I just said, why don't you try them out? And next thing you know, he had this made into a stepper that he put on a wristband to actually count his steps. So as I said, children are capable and competent of complex thinking. So when you start a new project, this is the screen you'll get. You'll have, what's really nice feature about the MakeCode editor is that there's a simulator for the microbit here. So if you don't have a microbit, or your school can't afford to purchase them, then you can still do these activities with the simulator. So on the left is a simulator. On the middle section is the blocks menu, where you actually get your programmable blocks. On the right is your workspace, where you actually build your code. And then down at the bottom of your screen there, you'll see download and saving. That's where you can actually download the program to the microbit and save it, so that you can actually make your microbit mobile by plugging in the battery. So without further ado, I'm going to pass it back to Cheryl, and Cheryl's going to speak to you about 2 activities, one on creating code so that this microbit becomes a light sensor, and also a temperature sensor, because we're going to use those 2 programs, or you can use those 2 programs in our design and build that we're going to do shortly. Cheryl?
Okay, thanks, Lynn. So as Lynn said, on the microbit, you have that 5x5 array that can not only emit light, but it can also detect light. So we're going to use it in this case to detect light. And the light level, usually, for those of you who might be physics teachers we know it's measured in lumens, but our microbit will actually not give you a lumens reading. It gives you a relative reading between 0 and 255, 0 being the darkest and 255 being the brightest. So let's look at the code for a light sensor. So as Lynn said, you have your block menu in the middle, and notice that it's all color-coded, and it's a drag and drop. So we'll start with the forever. you'll notice it at the beginning, Lynn had an on start and forever in there. You can either just click on the on start and delete it, or you can drag it over and drop it, and it'll just go into the trash for you. So once we have the forever block, well, what we're looking for is we want to see a number between 0 and 255 for our light level. So we're going to go again into basic, and we'll find one that says a show number. Now, what do we want to show the number for? Well, we want to show the number for light level. So that's an input. So we just click on that, drag it, and drop it over in the little circle that was there for show number. So it's going to show a number for the light level. Now, if we just left it at that, what would happen is the reading would be, it would continue to show the light level as it was detected by the microbit, but it would do it so fast that you wouldn't be able to see the LEDs being turned on and off on the microbit. So what we want to do is we want to put something in there that's going to cause it to slow down, and that's a pause, which is also in the basic. You'll notice that there's an arrow there, so there are some pre-programmed times there, but you can also just type in your own if you want, and they're in milliseconds. So you'll notice then on the simulator that's there, you'll see that the reading is 128 when this was done, and that would continuously scroll across your microbit for your light sensor. So that's your completed light sensor. So as Lynn said, we're going to look at using this in the design and build activity. So we want to make that light sensor portable. So what we need to make it portable is our microbit, the USB cord, the battery pack, and the 2 AAA cells to go in that battery pack. And what you're going to do is you're going to do what's called flashing the code to the microbit. And to flash the code to the microbit, you'll see it being simulated down at the bottom in the right. You're going to attach your microbit to your device using the USB cord, and then you're going to name your program. And in this case, right next to the download there, you'll see that it was named Light Sensor. Once you name it, hit the little save button that's right beside it on the blue, and it has been saved. But now what you want to do is you want to transfer that file to the download file on your computer. So you hit the download, and it will go to that download folder in your computer. Open the download folder in your computer, drag and drop that light level folder that will appear there as a hex file, and you drag and drop it from your download folder, and you drop it onto the microbit, which you'll find located under your devices on your computer. When you do that, you should see on the back of the microbit an amber light flashing, and that indicates that the file has been downloaded. You then unplug it from your device, and you attach it to the battery pack. Don't have it attached to both the device and the battery pack at the same time. So that's what we mean by flashing. Now, Lynn said also up there you'll see if you're using a device, another device, you can also find information at this bit.ly link for pairing it to a Bluetooth. And some of you will probably already have your devices set up so that you have Bluetooth pairing, so it would be very easy for you to be able to do that. But you can see how to do it if you access the document at this link. So the other sensor that you're going to use is the temperature sensor. So we're still going to have that forever. We still want a number showing for the temperature, but now we're going to get rid of that light level. So we're going to remix this, and what we're going to do is again go to input, find the temperature block, and insert it there. And again, we want it so that we're able to read it, so we put that pause in there, And our microbit is capable of reading temperatures in the range of about -15 degrees Celsius to about 50 degrees Celsius. So that's your temperature sensor. There are 4 other challenges here, and Lynn talked about the A button and the B button. So these are challenges where you can remix this program to use your A button and your B button. I'm not going to go through all of those with you today, but you'll be able to access them through the recording. You'll be able to see them and be able to use them. And again, debrief is really important in order to consolidate the learning. And again, you're going to go through those skills. Did they break it into smaller parts when they were doing? Did they create an algorithm, steps? Well, there were steps for that program. Did they have to evaluate, test and evaluate? And your simulator was there to help you do that. You knew whether your program was working. If it wasn't working, then you had to debug it and start again. And obviously, you were thinking critically, you were being creative, and you were being self-directed. So I'm going to hand it back to Lynn so she can talk to you about how to integrate this into a design and build.
Okay, so we spoke about computational thinking right from the beginning, and how it is important to, one of the approaches is designing and building and creating things. And I'm a firm believer that too often we give children answers to remember rather than problems to solve. So let's give them a problem to solve. And we do that by using, and I guess, building in a problem to the design and build process. So there's different variations of this everywhere. You'll see it different places, but the gist of it is that you give children a problem, and a real world problem is a great idea to have one. But there are lots of places to get ideas for problems, from literature or from, everyday life, from your school setting. And then getting students to research and generate ideas that they have, like working together and generating some brainstorming. And then they come up and sketch or plan what they're going to actually build, like an engineer would. Then they actually create it or prototype it. And by far the most important step in this whole process is the testing and evaluating. In other words, does it do what it was meant to do? Does the prototype work? And if it doesn't work, then children should be encouraged to go back and make the changes required in the prototype to actually make it work. That whole idea of perseverance comes in there too. And we always get students to do a gallery walk where they reflect and share the product that they created. So which problem are we going to do today? And we're going to get our provocation from a book. And the book is The Lorax by Dr. Seuss. And the quote says, unless someone like you cares a whole awful lot, nothing's going to get better. It's not. So if you're familiar with the book of The Lorax, it's really about the Onceler and a group comes in and does environmental damage beyond any level to a certain community, and all the truffula trees get killed or I guess cut down. So one of the segments from the book, it says, at that very moment we heard a loud whack. From outside in the fields came a sickening smack of an X on a tree. Then we heard the tree fall, the last truffula tree of them all. So they did so much industry, I guess, that now there's no truffula trees left. So toward the end of the book, a little boy shows up in the community and he's so sad about it, but the Onceler has something for him. He says, catch, says the Onceler. He lets something fall. It's a truffula seed. It's the last one of all. You're in charge of the last truffula seed, and truffula trees are what everyone needs. Plant a new truffula, treat it with care, give it clean water, and feed it fresh air. Grow a forest, protect it from axes that hack. Then the Lorax and all his friends may come back. So the problem identified in that literature, and of course you don't have to use that book, you can use different books for coming up with problems or problem ideas. So our problem here is the last truffula seed must be protected. So our challenge to the students is use the materials provided to design and build a structure that will protect the last truffula seed. You can use a real seed, like a pumpkin seed, for this activity. We often use little pom-poms to reflect the seed. So this is a real world example of the exact same thing. Not sure, I really wasn't aware of this actual Svalbard Global Seed Vault until a couple of years ago. But halfway between the Arctic Circle and Norway is an island with a mountain, and inside that mountain, they have built a seed vault, and it holds the, I guess, 13,000 years of agricultural history in one room. So just in case there's a global catastrophe and we lose seeds, then seeds from all over the world are housed here so we can actually preserve them. So it's lovely to bring that in as a real world example for kids. So what does our seed saver have to do that you're going to get students to build? It must have use 5 or different materials, 5 to 10, sorry. We always love to put a numeracy focus on it to limit the materials, because that's typical of an engineer having limited money to use in terms of producing something. So use a maximum of $10, and we use less toxins, play money for that. The seed must be protected from extreme heat, cold, wind, and water. It must be in a closed container, and this is the catch that links what Cheryl was talking about to this actual activity. You can leave it here and get students to actually do it with a thermometer, but we like putting in some kind of a data collection tool, if we can, digitally, so that we can control or determine if the seed is being protected from the environment. Has there been a change in the temperature or the light level inside that structure that the students build? So we want to incorporate the microbit. Excuse me. So we just use everyday materials for the actual building of the seed sorter, or the seed saver, like craft sticks and ribbon, pipe cleaners, toothpicks, elastic bands, just regular material. And of course, we get them to work in teams. And first of all, they got to choose their materials wisely in keeping with that $10 budget. They sketch out what they're going to actually build. They choose the best sketch and build or prototype that structure. And of course, the most important thing, they have to test it. So they might want to test it, for instance, in a fridge or outside or in light levels or high light levels. And of course, we always get them to share. These are just some examples of some prototypes that some educators did at another workshop we did in Toronto not long ago. So you notice the microbit is built in, and one group actually even had the microbit, and here you'll see it actually embedded underneath the tin foil. But one group actually had 2 microbits used, where one microbit could transmit the information to the other. So they actually embedded it right in the prototype, which was fantastic, we thought. So they radioed one microbit the message to the other. So we always get students to reflect and share their ideas, and when we do a workshop with teachers. So we had you face-to-face where you'd be actually building that seed saver, putting your microbit in there, programming your microbit for temperature and light. And we'd be asking you, does that prototype that you created solve the problem? Does it meet the design criteria that we outlined to you? You know, did it use like a minimum of 5 and maximum of 10 materials, for instance? And what ideas do you have to redesign or modify it? So get students, if you're doing this activity, and I encourage you to do it because I've done it with a group of grade 4s and they loved it. And it fits in so well with integration in the curriculum in terms of the things that, you know, seeds need to, be protected and what they need to actually live and germinate. So what happens if we put our seed saver in the fridge, in a sunny spot, in the cupboard, in a greenhouse? And of course, it's so important that we get students to collect the data that's recorded on their microbit and demonstrate it or show their learning somehow. It can be in a bar graph or a chart or a line graph, but get them to actually record the data that they actually receive. And I'm going to pass it to Cheryl for the final piece on cross-curricular connections for us.
So when we do an activity like this, we like to point out that there are connections with other subject areas. For example, when you're doing something, well, the obvious connection to literacy, of course, is using children's literature as your provocation for this Design and Build challenge. But also, you're asking questions. You might ask them, what's a good way to organize seeds? There might be a number of seeds that you give them in, or what materials are good for keeping things dry, or what kinds of things do seeds need? what do they need to be protected from, and what are some ways we can protect them? And obviously, when the students are working together, they're going to be communicating with each other. They're going to be sharing their thoughts and their feelings and their ideas with each other, brainstorming their ideas for the seed saver. In terms of mathematical thinking, well, Lynn already pointed out the collecting and displaying their data and choosing an appropriate method of displaying the data that they collected. But also you're getting them to sort and classify. You could ask them to sort and classify seeds. You could also ask them to look for similarities and look for differences in terms of the seeds that are being saved. And Lynn gave the real world example of the Svalbard vault, seed vault. And you could talk about the seeds that are in there and what kinds of seeds are there. And also you could ask them to put them in order. So from largest to smallest or smallest to largest. With visual arts, well, one of the things that we ask the students to do in this project is to sketch their design that they're going to prototype. And then they represent it and they model it. They make the design and they build a prototype from the sketches. So there are a number of connections with other subject areas. Now, if you want to extend the learning, we talked about at the very beginning some of the programs. Well, two of the programs that we have, one is called Tomato Sphere, which is our Seeds from Space program, and we also have our Living Space program. This would be a great way to extend the learning, taking it to a space environment. For example, would your seed saver be the same or different if it was on the International Space Station, or if it was going to Mars, or if it was on the surface of the moon? And also the Tomato Sphere, as I said, is our Seeds from Space program, and then Living Space is actually connected to, here in Newfoundland, it would be the grade 6 and the grade 9 curriculum, and looking at environmental conditions necessary, to be able to survive in space and conditions on the ISS. And last year we actually partnered with David St. Jacques and for this Living Space program when he was on the ISS, and classrooms around the country collected data on environmental conditions, and he collected the same ones on the ISS. And so they had lots of data to work with. So to wrap up, this brings us to the end of our webinar. Please, if you have any questions for us, just pop them into the chat and we'll answer them. Please check out some of the other learning opportunities, professional learning opportunities that we have. We talked about the digital handout, and you can access that using that bit.ly link, and the password is LTSDL 2019. Also, we'd appreciate your feedback, because your feedback always helps us to better our practice and improve our practice. So there is also a bit.ly link there for the short survey. And please stay in touch with us. And the ways that you can stay in touch with us is we have a Facebook page. We also have Twitter. We have a YouTube channel. You could follow us and our volunteers that we have on Instagram. And of course, you can always email to contact us directly at professionallearning@letstalkscience.ca. And we wouldn't be able to provide any of these without our supporters. So I'd like to thank our national professional learning supporters, who are the Government of Canada, Dow, Jacobs, Nova Chemicals, and SAP, and also our digital literacy supporters, the Government of Canada, the Canadian Space Agency, and SAP.
Cheryl, I'm just going to go back to the slide for the digital handout.
Yes.
And I'll just leave it on for just in case people didn't get a chance to jot down the survey link or the access link for the digital handout, as well as the password. So I'll just leave that up there. So I guess we can pass it back to Remy, if he's there, if there's any questions in the chat or.
Yeah, thank you so much for your time, Lynn and Cheryl, for sharing these great resources, first and foremost, to give us a better understanding of computational thinking, digital literacy, and then sharing with us the microbit tool and working with MakeCode, and then all the great resources that Let's Talk Science has that are available for educators. Again, I want to take a moment to say thank you to Let's Talk Science and to Lynn and Cheryl for their time and dedication and partnership to making this available. And again, this whole session has been recorded and will be available for all educators to revisit and review if you're okay with that. And then looking forward to having you participate in future workshops with us. Again, the workshops for Let's Talk Science, as well as for many of the other partners, are available at www.logicsacademy.com /virtual training, and I'll be sharing that in the chat here in case you're not as familiar with it. And through there as well, you'll be able to see a link where you can go to our YouTube channel, and you'll have access to all the recordings for this virtual training, as well as many of the other ones as well. So you'll be able to see the playlist of the virtual training series and be able to replay and rewatch this. So this will be available by end of day today once it gets uploaded and put on there. And again, if you have any questions, feel free to just unmute yourself and ask the questions out loud here in the group. Or again, you can use the chat function to link in. So I hope you enjoyed this session, and I definitely learned a couple of new things that I didn't know about. So this is wonderful. Thank you so much.
That's good, Remy. Thank you.
Thank you.